I'm waiting for exactly 2:15 so that the webcast people don't get upset that we started early. Anybody got an atomic clock? Yeah.
8 seconds.
Thank you. All right, good afternoon, everybody. Welcome to our Tuesday afternoon press conference on the Sloan Digital Sky Survey here in Seattle. I'm Rick Fienberg, AAS press officer, and I'm very excited to see that press conference after press conference we're filling the room. It's very gratifying. And that's a good thing because there's lots of interesting news happening here. Before we get started, I'd like to remind you all to silence your electronic devices so they don't start ringing or beeping or otherwise going off during the briefing. Normally, I introduce the speakers, all of whom then speak in order, followed by the Q&A, but I'm actually going to turn it over to one of our speakers up here on the panel to do the introductions. So let me just give a quick rundown of what the subject of the briefing is, and then I'll turn it over to Michael Wood-Vasey. You hear a lot of talk at this meeting and in most astronomical contexts now of the coming generation of big surveys. Astronomy of the future, actually astronomy of the present and the very near future, is a lot about giant surveys, big data, looking at the whole sky all the time, looking for transient events, counting up stars, galaxies, and other things. But actually, the astronomy of the not too distant past has been about surveys too. The Sloan Digital Sky Survey in particular is the first large-scale electronic survey of the sky. It's been producing landmark scientific results for many years, and we're going to hear about its latest incarnations and latest results today. The scientific spokesman for the Sloan Digital Sky Survey is Michael Wood-Vasey of the University of Pittsburgh, and I'm going to turn the podium over to him to introduce the speakers. Let me just remind you that if you are on the webcast, please log into the text chat, and my deputy press officer, Inga Heyer, will relay your questions to us at the end of the briefing. All right, Michael?
Thank you, Rick. Good afternoon. Thank you for joining us for the briefing. I'm Michael Wood-Vasey, the Sloan 3 scientific spokesperson, and we are here today to announce the final data release from the third incarnation of the SDSS survey, the Sloan Digital Sky Survey, which has encompassed 4 key aspects, probing different phases of our universe, from looking for exoplanets around nearby stars, to looking at stars in our galaxy, to looking beyond our galaxy. And today we have 4 presenters who have each played such key important roles, and they'll be telling you about that today. We have Connie Rockosi, who's the principal investigator for the Segway survey of our galaxy and has been just such a key person involved in the hardware for Sloan for all of its life. Daniel Eisenstein, who will be summarizing the cosmology results from BOSS. He's the director of SDSS-III. Next, we'll have Jian, who's the principal investigator for the MARVELS project that's looking at exoplanets in our own galaxy using some new technologies. And continuing that new technologies theme, Steve Majewski, who's the principal investigator of APOGEE, will be presenting and summarizing the results from the new infrared spectrographs that have allowed us to probe our own galaxy. So thank you for coming. I hope you will enjoy and look forward to the data that are coming out, not just for the science interests we have, but really the theme of the public data for everyone. Connie?
Sorry, just hit the reset button, and then double click on Eisenstein when it comes up.
Okay, so my name is Connie Rockosi, and I'm delighted to be here today to tell you about the Sloan Digital Sky Survey Project's 12th data release. So this is the latest and the final release from SDSS-III, and to give you some idea of the scope of what's in this data release, there are 5 million spectra of astronomical objects, imaging information on 470 million galaxies and stars, and the whole thing weighs in at 117 terabytes. So the SDSS has been surveying the sky since 2000, so we've been at this for 15 years now, and giving away the data all the while. The first public data release from the SDSS was in 2001, and we're now on data release 12. So SDSS-III, which is who we are and who is bringing you DR12, in which you'll hear about the science programs from that, started in 2008 and ended just this past summer, and so now we're ready to release the final and the full SDSS-III data set. So the SDSS-III surveys, like the other Sloan surveys before them, have been taking advantage of and using what's been a leading and a very productive wide field survey facility in astronomy, and indeed SDSS-III has helped add new technologies to increase its scientific reach. And SDSS data have had, over the course of this time, impact on nearly all topics in astrophysics, and the public data have had their impact as well. There have been more than 6,000 papers written using the publicly released SDSS data. So SDSS-III consists of 4 different surveys, ranging in science goals from BOSS, which is looking at the very distant universe and set out to measure the expansion of our universe over the past 11 billion years of its history. Coming closer to home, the MARVEL surveys searched for exoplanets around nearby stars, and the APOGEE and the SEGWAY surveys studied stars in our galaxy to learn about the history and the formation of our Milky Way galaxy. So the theme, the tool that all of the SDSS-III surveys have used and what they've done with this wide field spectroscopic facility is to use the data, to use the instruments and the telescope to disperse the light from the objects in the field so that we can measure not only how much light an object, a star, or a galaxy is giving out, but how much at different wavelengths, red or blue. And by recording spectra and using them to make measurements, we can get at all the science goals of the SDSS-III surveys. We can see the tiny gravitational tugs that planets exert on their host stars and use that to find exoplanets. Measure the element content of stars in our galaxy and of other galaxies. Use the speeds of stars to weigh our Milky Way galaxy, find out how much total mass there is, and watch the accelerating expansion of the universe by measuring the redshifts of distant galaxies. And the science goals of the SDSS-III surveys, the push to make more precise measurements, to go to find exoplanets as well as distant galaxies, to observe our galaxy and do sky surveys at new wavelengths, has been enabled partly by new technologies that we've been able to add to the Sloan Foundation telescope and its instruments. So we added a new fiber system, and the fibers are the squiggly red and blue objects there that take the light from the objects in the very wide field of our survey telescope and allow us to take spectra of many, many objects at once, which is what gives us our sort of survey efficiency and the survey grasp of this facility. New technologies for the dispersing elements, the optical elements that make the spectra for both the infrared and the optical spectrographs, allow us to disperse the light, to make more precise measurements than previously, to allow us to survey the sky in new wavelength ranges, and to detect the light from ever fainter objects. And new detectors to record those spectra let us look at fainter and farther objects and get more precise measurements than ever before. So this is a public data release, DR12, which means everything is available to everyone, to scientists, to other astronomers, to students, and to anyone and everyone who's curious about the universe. And we have various portals and interfaces that you can use to get at the data. This is a picture of the Science Archive server, which lets you download images and spectra for yourself. You can make your own measurements and see what you see and see how it compares to the catalog measurements, which you can also download. So these are the measurements that the surveys have made on the data in order to enable their science. There's also the Sky server, which has tools so you can explore the data, link the various measurements on an astronomical object, link the imaging and the spectroscopic data. You can learn about some of the science and how it's done with tutorials and follow some examples. There are student exercises, and you can search the database yourself to pull out the objects that you're interested in studying and understanding. So the 4 surveys that you'll hear about today, the public data release, the science that will be presented here and elsewhere at this meeting, are the work of 1,000 astronomers from more than 50 institutions around the world. So a lot of people have put a lot of their time and energy into making these surveys happen and then releasing the data. This is the acknowledgments both of our funding agencies, to whom we are very grateful for getting us here, and all those institutions which have really put their time and effort, and their scientists and staff have put their time and effort into making this survey happen. So just to sum up, Data Release 12, which we're here to announce today, is the largest SDSS data release so far. It contains data that make more precise measurements than before, new kinds of data and new wavelength ranges for the survey facility, and new techniques for making these measurements. So we've expanded the science in SDSS-III in this new data release. DR12 was the final data release of SDSS-III, but we know that the science that will come from the data is just starting to happen. The collaboration is still working, and we know that much more science will come from the data now that it's been made public for everyone to use. And this is the last data release from the SDSS-III project, but there's more to come in the future from the SDSS because the SDSS-IV survey program has just started.
Okay, I'm Daniel Eisenstein. I'm the director of SDSS-III, and it's my pleasure to tell you today about the Baryon Oscillation Spectroscopic Survey, BOSS. This is an experiment to probe dark energy with the world's largest extragalactic redshift survey. So first, let's talk about what a redshift survey is. When we look up at the sky, we see galaxies and stars and quasars, but we're only seeing their two-dimensional position on the sky, and we would like really to turn this into a three-dimensional map. The way that we do this is by taking spectroscopy of those objects, measuring the redshift, and that allows us to infer something about the relative distance. So that allows us to turn pictures of the sky into three-dimensional maps of the large-scale structure of the universe, where we can see what's called the cosmic web, or the large-scale filamentary structure of the universe. And BOSS is the largest such survey, making the largest volume and most detailed map, and that full map is now available in data release 12. So the key science goal for BOSS is this topic of dark energy. That's the acceleration of the expansion rate of the universe, discovered in the supernovae experiments about 15 years ago. And this remains as one of the great mysteries in modern physics, the idea that the expansion rate is actually accelerating. BOSS allows us to study dark energy in a variety of ways, but the most powerful way, and the namesake of the survey, is this concept of the baryon acoustic oscillations, where we can use the clustering of galaxies to measure the distance, the relationship of redshift to distance, and thereby measure the expansion history. Now, the distance-redshift relation comes about because in an accelerating universe, objects at a given redshift are a little bit more distant than in a decelerating universe. And by being more distant, that means that they're fainter, so the supernovae at those redshifts would be fainter. In our case, objects of a given size will appear smaller. So the way that we do this with this thing called baryon acoustic oscillations arises because of sound waves that propagate in the early universe, the first 400,000 years after the Big Bang. And these sound waves imprint a very characteristic signature into the clustering of galaxies. The signature has a scale that we can calculate, and that allows us to infer distance by using something called a standard ruler technique. So the idea is very simple. If I tell you that I'm 6 feet tall, then you, by sitting in your chairs, can measure the angle between my head and my toes, and from that determine how far I'm standing away from you. In this case, the characteristic height is this tiny effect from the sound waves in the early universe. And these sound waves produce a small extra correlation in the clustering of galaxies. So if you're sitting in one galaxy, then it is slightly more likely that for there to be a galaxy 500 million light years away from you, as opposed to a galaxy 400 or 600 million light years away from you. And BOSS has now detected this effect with unprecedented quality, and we've used it to measure the cosmological distances to 1%. Now, the challenge of BOSS is that this length scale of 500 million light years is large even in the context of astronomy. And that means that we're driven to use very large survey volumes. So BOSS has now covered 25% of the sky, and we've mapped 1.4 million new galaxies out to a redshift of 0.75. But putting that in more conventional terms, this is equivalent to mapping a volume of the universe that's a cube, with each side being 8.5 billion light years. So that's the scale of the universe that we've measured, the size of the scale of the volume of the universe we've measured. And in addition, we've used quasars at even higher redshift, and the sight lines of these quasars are probing through the universe, and this allows us to make a map of the universe reaching back to 11 billion years into the past. So I think the cosmological highlight from BOSS is the detection of these acoustic oscillations, and this gives us a very direct link between the physics of the microwave background anisotropies, the things that are seen in the WMAP and Planck satellites, a direct link between that physics and the physics of the clustering of galaxies in the recent universe. And that link has allowed us to give a very strong confirmation of the existence of dark energy, and at this point we have no detectable deviation from the cosmological constant model. So in other words, the dark energy density appears to be constant over time. We've also been able to measure the shape of the universe, the so-called curvature of the universe, and we found that curvature to be negligible, meaning the universe is very close to a flat cosmological model. That's shown in this slide, where on the bottom axis we have the curvature parameter, so how flat is the universe, with 0 being flat, and on the vertical axis, how constant is the dark energy, with W of -1 being the cosmological constant. And the blue region is showing the combination of BOSS data with Planck data, and you see a very small contour which centers in on the flat universe with a cosmological constant model. So this is a remarkable thing. We've now tested cosmology opening up 2 degrees of freedom, and the data has driven us back to the simplest case of a flat universe with a cosmological constant. So with data release 12, we're bringing BOSS now in full to the public, and the total number of optical spectra from SDSS over the past 15 years now totals more than 4 million spectra. That includes 2.2 million galaxies and 400,000 quasars, and both of these numbers are over half of the world's total of galaxy and quasar redshifts. So this is really a vast data set, and it's been a great pleasure within the collaboration to analyze it. But now I think the legacy of the data set for the public will be equal or larger, and so we're very happy to announce it today. Thank you.
Hello, everyone. So I'm Jian, the principal investigator of the Marbles survey of the Sloan 3 program. And this survey basically takes advantage of the new Doppler technology and with the wide field telescope of Sloan, and to enable observation of 60 stars in single observations. So that basically means increase the great speed of the survey and the ensemble size to enable to a big size of the survey. And here, just to remind you, the Marble is basically to measure the Doppler shifts of the stars, and so to basically to sense the motions from stars and able to measure the companions. And because of use this new technology, so we allow to obtain a largest data set in history, and with radio velocity and over 5,500 stars, and that's released through this time. And to remind you, the Doppler technique pretty much is measure the stellar lines shifts caused by the unseen companion around stars. So basically, by see the lines, blue shift and red shift, and then you can determine the mass of the companion and also period of the companion. And based on the amplitude, you can eventually measure the companion. Is either binaries or brown dwarf or giant planets. So therefore, the Marbles pretty much use this kind of technology to measure that. And so because of the new technology, so therefore we set a goal to have the accumulate the largest systematic data set of well calibrated radio velocity measurements of nearby stars, and so that way allow to study systematic study of giant planets, brown dwarf, and binaries populations. And because the sample is so big, so therefore you can imagine such a survey, and you can allow to probe the very big range of the mass and object distributions among the stars with all kind of properties. For example, different mass, different age, different compositions, and also even different environment. For example, single stars, multiple stars, and also even go to the metal poor and old thick disk, for example, in the Milky Way, which is usually difficult to approach by the other technique. And so because of that, and the sample is very diversity and with different kind of properties. So therefore, these data sets can really able to use for testing the planet formation migration evolution kind of models. And to remind you, how these marvels can enable such a big survey, this is use a new technology and take advantage of the interferometer and allow to observe 60 star Doppler shifts in a single observations, as compared with to the traditional shell Doppler technique is only allowed to observe one star one times. So therefore, this basically technology allow to greater speed of the survey, and also allow to give to observe many objects simultaneously. And through this data release, and basically, as I mentioned earlier, so it allow us to release the measurements over 5,500 stars and about almost 100,000 Doppler measurements over the 4 years in 2008 and 2012. And the majority of the stars observed more than 20 times observations. So therefore, you can use that data itself to do your own studies of stellar companions. And this data set alone actually already doubled the entire radial velocity measurements by any of the previous radial velocity instruments in the world. And because of this new technology, and the key of this data set is we provide a very homogeneous data set, because this single survey we have the unique and very classified the strategy. So therefore you can use that for test planet formation. And here I just show you examples. And here's the earliest release of the almost 300 new binaries come from marvels. And if you compare with the previous single radial survey for binaries, you can see that right now marvels already provide 4 times large samples. So therefore, this sample is already big, so you can use for static study of the static properties and the distributions, and also you can use test the binary formations. Actually, which is one of the now is hottest area for studying star formations. And talk about brown dwarf and giant planets. And here I just want to show you the plot. Here is the landscape of entire known giant planets and the brown dwarf. And you can see here on this diagram, you see horizontal lines is basically is a mass division between the giant planets and the brown dwarf. Above that will be brown dwarf, and below that will be giant planets. And in the planets field, you can see here there's 3 groups. As you probably notice, one is the very close, a few days period, usually we call hot Jupiter kind of populations. And on the far distance, on the right side is giant planets like our Jupiter. And then below that is the one is recently discovered by Kepler and also ground-based radial velocity called the closing super Earth. And from this population, you can notice the brown dwarf is pretty much called desert. It's very few. But marvels now already able to, with 38 discovery from this released data set, you can see here right away double that areas. And then you can see we also have the 51 giant planet candidates released, and also that will occupy these 2 populations, hot Jupiter and distant Jupiter-like planet. And with, of course, with future further improvements of the data processing, we should be able to put it down and able to contribute significantly in these top left corners, and to allow study the diversity of the planet populations. To illustrate how the marvels can do unique things, and here I'll just show you example of the discovery from the marvels, and we call strange solar system. As you can see here, is a pair of sun-like stars and in Leo constellations, and with 2 stars, and we found 2 companions, and one is giant planets and one is brown dwarf around its primaries. And this is the first time ever detected in such a closed system. And because these 2 stars are only within like a Sun and Neptune distance in our solar system. Think about it. If you in solar system have 2 of these stars, you almost can't imagine you can form planets, right? But we found this is so unique system in marvels. And if we compare with all the previous one, and of course, you can notice, they all have single one. And the most famous one you probably notice is called Alpha Centauri. That is debatable, and it's like Earth mass planets around that one. But suddenly now, our detection is so unique because you got 2 in such a very packed environment. So therefore, this indicates what happened with these formations. So therefore, this is pretty much the marble detections already challenge the current, planet formation theory and see how they form. And because the traditional theory, they always build up, from dust accumulations and go up to the more massive, giant planets. But this, because it's got this companion nearby, so it's disturb the whole environment. How they form is really challenging. So this, therefore, is indication marble is already able to produce this kind of unique discoveries. And here, just the artist's impressions about how this system looks like. And you can imagine, primary is like sun, like stars, and you can see the nearby one is only, only a 10 days period. Giant planets very close. It's scorched by the radiation from the primary, and then you see a little bit distant companion is brown dwarf companion is more like in the Mars orbit, and then you can see far distant in the background is a secondary. And this is pretty much indicate marbles really can, the data sets we released and can open up this kind of major, discoveries and studies. And here I want to conclude marble survey, and through today's data release, we'll provide the largest data set of pre-seen radio velocity to the community, so people can use that for their own studies of this different kind of population, from binaries, planets to brown dwarf, for example. And also, because marble survey is the biggest survey in the history, so they also provide complementary work to the ongoing surveys such as Kepler and Gaia. Those they probe the different kind of population of planets, and also the ongoing future surveys like NASA test missions, and also ground-based like imaging and macro lensing. And not only that, but also marbles, because use new technology, emphasize new technology. So therefore, this new technology enable many objects observed same times, unlike the traditional technology, only single object one times. So this basically opened up a major door for radio velocity to open up, very big survey for future. Many stars can be observed with this technology to enable discover many of the giant planets. Thank you.
Hello, my name is Steve Majewski, and I'm here to tell you about the Apache Point Observatory Galactic Evolution Experiment, or APOGEE. APOGEE represents, in several ways, new direction for the Sloan surveys. First of all, whereas the previous surveys that Sloan has been largely driven by extragalactic work, previous surveys have tended to avoid the very densest parts of the sky, of the Milky Way on the sky. Since we're a survey that is interested in the Milky Way, we're probing those very regions that have been previously mostly ignored. But secondly, with new technologies, we are actually probing a new wavelength region for Sloan, and that is the near-infrared, and producing spectra with 10 times greater detail than the previous Sloan spectra. So the Apache Point Observatory Galactic Evolution Experiment, the driver is to create the first comprehensive high-resolution spectral survey of all the parts of the galaxy, all the populations of stars that are in our galaxy. And whereas there have been previous surveys that have attempted to do this, ours is fully comprehensive in accessing all parts of the galaxy. And the reason that this has been a problem before is that the vast majority of stars in our Milky Way are hidden by large blankets of dust. So if you zoom in on this optical picture of the galaxy, the central parts of the galaxy here, you see these large black voids here. They're voids because those are foreground dust clouds blocking the light of stars that are behind. And as we saw in the press conference yesterday on the Eagle Nebula, through using infrared radiation, we can penetrate those dust clouds and see the stars behind. So we can compare this optical view of the galaxy to an infrared view, and you can see much more clearly the actual distribution of stars in our galaxy. And so looking at infrared light, we can actually get a better idea of we can actually access all the parts of the galaxy and see it much better. So the APOGEE survey was enabled by the creation of this new technology, state-of-the-art spectrograph, and the ability to take high-resolution spectra in the near-infrared for 300 stars simultaneously was only possible by breaking several new technologies that went into the instrument here. And this is a picture showing the installation of the APOGEE instrument on site at Apache Point Observatory in the spring of 2011. So this is a plot showing the sections of APOGEE spectra. So what we have here on these these two wiggly lines here are the relative brightnesses of the stars as a function of wavelength. And the various dips here are showing the absorption of specific wavelengths of light by certain types of atoms in the star. And each particular atomic species has a characteristic pattern of lines or wavelengths that it wants to absorb. High-resolution spectroscopy allows us to see these dips in very fine detail and allows us to make very accurate measurements of the chemical compositions of the stars. So at the bottom of the plots, you see some of the representative chemical elements we're accessing with APOGEE spectra. And by measuring the lengths of these dips, how strong the dips are, we can get a measurement of the amount of the number of atoms of each chemical species in each star. So, for example, the black spectrum here has many dips in it, and that shows that there are many heavy elements in this star, and that shows that this star has been formed after many generations of stars have existed in the galaxy, creating many generations of chemical elements put into the creation of this particular star. The red star has fewer dips. It has 100 times less iron and other chemical elements in it, showing that it, in fact, is one of the older generations of stars. It's a member of one of these earlier generations that contributed to the formation of the black star there. So in DR12, we're releasing data from all of the APOGEE observations that have been taken place in the last 3 years. And this includes 500,000 spectra of 156,000 unique stars. And as you can see from the distribution here on the sky of where we've pointed, the green dots are the APOGEE fields, you can see that we've deliberately tried to access all the different galactic environments that there are and that we can access from New Mexico. When we analyze the stars in detail, we can actually ascertain their intrinsic luminosities, and from that we can actually ascertain their distances. And so this is a plot showing a top-down view of the distribution of stars in the APOGEE survey projected onto the plane of our galaxy, and we can overlay an artist's conception of what the Milky Way looks like, and you can see that the distribution of APOGEE stars actually accesses most major structures of the Milky Way, or all major structures of the Milky Way. So I mentioned before that by looking at the dips of the lines in the spectra of stars, we can understand how many generations of stars have contributed to the creation of any other particular star. But that doesn't tell you the pace, the length of time associated with each generation of stars. So we don't know whether those generations were very short or very long. But we can actually ascertain that information by looking at the detailed chemical compositions of stars. And by looking at the detailed chemical abundance patterns in stars, this DNA that is intrinsic to each star, we can actually tell the ancestry of the star. So, for example, this is a plot showing the relative oxygen content in APOGEE stars. So this is the APOGEE sample in DR12, and we can see the distribution of the amount of oxygen in each star relative to the sum of all heavy elements in the star. And we can see that there are two major populations represented here. The upper plot here is from stars that have been created from generations of stars that largely had heavy elements produced from dying massive stars. And these massive stars live short lives, and so these generations are very quick. So those stars are formed relatively quickly. And the bottom population is very black region here where there are many more stars. Those are stars that were formed with many contributions from generations of stars where the heavy elements were produced from exploding white dwarfs. And those take longer to live and die, and so those generations have a slower pace. And so we can learn about the ancestry of the stars by looking at these kinds of plots, of which this is just one example that we can create with APOGEE data. So this is an edge-on view of our galaxy. The circle is meant to represent approximately the location of the sun in our galactic disk. And the size of that circle represents the approximate volume that has been previously probed by other surveys with the quality of spectra that we're producing in APOGEE. And of course, we're now, as I showed in the earlier plot, accessing across that entire region that we're seeing there. And so we can just, in broad brushstrokes, show you that same ancestral DNA plot that I showed before in these four general regions. And you can see that the plot looks very different in different parts of the galaxy. And this is just a representation, a broad brush view of the kinds of things we can do with apogee data, and we can actually interpret these plots just simply in a simple terms by seeing these kinds of data. We can actually interpret them as saying that the inner disk and the bulge of our galaxy formed more quickly than the outer disk of our galaxy. And these are very large boxes that we've drawn here. Of course, with apogee data, we have so much apogee data that we can zoom in on different regions and perform this kind of analysis in much smaller volumes across the galaxy. So apogee has concluded in Sloan Digital Sky Survey 3, but really it's just beginning because the analysis of the data is really coming alive right now. And in fact, even though we've done 156,000 stars, that's just scratching the surface. Apogee will live on both in the analysis of the Apogee 1 data, but Apogee 2 is a new project that launches off of Apogee 1 and is part of Sloan Digital Sky Survey 4. As you see in this plot, there were areas of the galaxy that we can't access from New Mexico because the Earth blocks our view. So we're going to solve that problem in Apogee 2 by building a second Apogee spectrograph that we're going to place on the DuPont telescope in Chile. And that will allow us to access the entire galaxy. So from this view that we've gotten in the DR12 data, we are actually going to, in the combination of Apogee 1 and Apogee 2, actually probe fully the disk of the galaxy in all parts of the sky. So in conclusion, Apogee in DR12 is presenting us already a major new view of the galaxy. We're presenting all of the raw data and the process spectra, as well as our derivations of chemical properties, 15 different chemical elements for over 150,000 stars. These are being used to create the most comprehensive maps of the chemistry of stars in our galaxy. As I mentioned, the analysis of these data are now happening we've got the data now. We're actually doing huge statistical analyses. There are 2 oral sessions tomorrow that are talking about new results from Apogee data. On Thursday, there will be another press conference representing exciting new results on another aspect of Apogee, studying the interstellar medium. But all of these data together are going to give us new insights into the formation of our galaxy using chemistry as the tool. Thank you.
Continuing the theme, what has allowed all the generations of these spectra are these wide fields of view. So this is 7 square degrees on the sky, projected from the telescope. And we select the targets based on imaging from Sloan, but also from 2MASS, now particularly for Apogee. And we drill a hole on each place where we would like to take a spectrum. And then people plug those fibers into each hole. There are 1,000 on a boss plate. And we've observed. So each one of the 5.3 million spectra that we're putting out in Sloan are a fiber that someone plugged into one of these holes and was then observed. For some of the other programs, we've done the same things for Marvels and Apogee. And in fact, we've run Marvels and Apogee together with using same plates with different holes plugged in, going off to the different spectrographs. And so that's just another example of the fundamental technologies, but also the new technologies that really allow these wide field surveys. Thank you.
Thanks to all of you. Thank you, Michael, for shepherding that through. We're going to take questions now from the audience here on site, and also we'll queue up some questions from the webcast viewers. If you are on the webcast and have a question, please ask your question via text chat. I want to remind you to please wait for a microphone. Deputy Press Officer Larry Marshall here will bring it to you. When you get it, please state your name and affiliation, and that way the webcast audience will know who's asking the questions. All right, so we'll start with questions. Down in front.
Monica Young with Sky and Telescope. This is a question for Daniel Eisenstein. I was wondering if you could just tell me a little bit about, I guess I was wondering about the one plot that you showed, which showed Planck data with the BAOs and then Planck with the supernovae. Is there a way to use just the BAOs, or do you have to use the Planck data as an initial condition to get at the cosmological parameters?
No, you can actually just use the BAO as well, but it certainly gives less precise constraints.
And does that agree as well?
Yeah, oh yes,
Okay.
it does agree. In fact, it gives very nice agreement. One of the opportunities in SDSS-III, because of the longer redshift coverage or longer time baseline, is that we actually now have enough data in the BAO to constrain the cosmology directly.
And just a quick other question. I know that you've measured BAOs at several redshifts. I was wondering if you could just remind me what redshifts you've detected the BAO at.
Yeah, so within SDSS-III, our primary measurements have been at redshift 0.32, 0.57, and then 2.3.
Okay. Thank you.
The exact numbers are not super important, so you might prefer to remember 0.3, 0.6, and 2.3 or something.
Just to follow up a bit on the first question, explaining the equivalent question of if you take out the Planck data or if you take out our knowledge of what the scale is. So Daniel mentioned that if you knew he was 6 feet tall, you could figure out how far away he was based on the angle. But if what you really cared about was the relative distance of how he had been getting farther away from you or things had been expanding, you don't need to know his height. You can just do this relative measurement. So we've been able, with these different redshift bins, been able to do this relative measurement that's also been consistent with this. And the more ways you check things and the fewer assumptions you have to make, the cleaner it is to be able to make these measurements.
Other questions here in the room? I actually have a follow-up question myself for Daniel. So you described your survey and what it tells us about dark energy. We've been hearing about some other surveys that are getting underway, like the Dark Energy Survey, and there's one at the Hobby Everly Telescope in Texas. What are those surveys looking for that goes beyond what you've been able to determine so far?
Okay, well, there's, as you say, there's many different cosmology projects going on, and at heart, I think there's a great deal of complementarity between them. So you mentioned the Hobby Everly Telescope Dark Energy Experiment. That one is more similar to what we're doing in SDSS-III. And in detail, they're using different technology, different sets of galaxies, but it is a spectroscopic program. So at heart, the type of data they're going to collect and the type of analysis they're going to do is relatively similar to what we do in BOSS. The Dark Energy Survey is very different because that's an imaging survey. So that's primarily going after gravitational lensing, measurements of supernovae, measurements of clusters, and they do a little bit of BAO, but honestly, it's really much better to do it with the spectroscopy. So these are very complementary things. We're really very eager to try to combine the data sets, and I think one of the big opportunities, both now and in the coming decade, is the combination of imaging programs with spectroscopic programs to further our cosmology. And I think the original SDSS was a great example of how imaging and spectroscopy really go hand in hand.
Okay. Any other questions here? Do we have any coming in on the web? All right, well then I'm going to take this speaker's prerogative and ask a couple more. I've got one for Jian. You showed a plot of different populations of exoplanets, including Kepler ones, and then you showed the addition of the Marvels ones. Since you've got a sample that's pretty well defined, are you able to say whether the statistics of the frequency of planets around certain types of stars is consistent with what had been seen in a survey like Kepler, or do you see any differences, and if so, what might that be telling us?
So right now, these are the early results, and the early results show basically is consistent with previous observations, especially with other radio velocity, and the brown dwarf also consistent with the previous one. But the key is, I pointed out, is Marvel was able to probe some of the very strange things system, and the previous survey not able to identify. But so far the static sense we haven't seen big difference, but the detail is always required follow-up, such as we already found a few in the very metal pool system, and that is haven't been found before. But we can't announce the discovery yet because we want to follow up, make sure those metal pool environments are they able to form brown dwarf or giant planets, for example. So this is pretty much Marvels eventually can provide to the community. So it's, probe some of the system nobody able to observe before, and then see what kind of population there in the rare situations, such as I showed this binary system, how the planets there.
Okay, and then a follow-up question is, Michael held up the plate, and we've heard, some surveys are doing 300 stars and some are doing 1,000 galaxies. What's the limitation that causes you, you were talking about 60 stars at once being a big improvement, but it's not as big a numbers as the other projects. So what's the limitation? Is it the population you're going after?
Well, no, the type of data that they're collecting is more detailed on each star, so they're actually choosing to use the pixels in the detector to basically put more pixels onto a smaller number of stars. So it's a choice to be made, but they're getting a richer data set about each star, and that's why they end up doing fewer of them.
That's right. So what Daniel said is radio velocity is unlike the spectra of the Bose or apogee. You get spectra, you get everything. And here, the all detail is come from these tiny Doppler shifts. So in order to get that, we have to design instrument, carry enough information.
Higher resolution?
Yes.
Okay.
That's right. And use interferometer, this new technology.
Okay.
That's the key things.
Somebody else has a question.
Yes, a related question. What is the wavelength range that you use for these planetary spectra, and what kind of velocity precision do you get?
Right now, the wavelength coverage is very traditional. It's in the almost like in the green wavelengths. It's like 5,000 astron to 5,700 astron, and very typical regions. In terms of precision, the photon we get potentially we can reach up to the 3 meters per second. It's not direct compete with currently the very high precision radio velocity doing single object, but this is give the big samples. That's the main strength of the marbles, to approach much bigger sample than anybody can achieve with single instrument.
Any other questions in here? All right, I have one more for Steve Majewski. You showed a map that showed you showed a map of the galaxy, Jian, with the location of the sun and the volume that had been looked at before in the much larger volume. And it reminded me of some of the same kinds of illustrations I've seen describing the Gaia project. And I'm wondering how the surveys that you've done up to this point, how they prepare us for Gaia, or how they complement the kind of data that we're going to have in that same large swath of the galaxy.
Well, of course, Gaia is primarily an astrometric survey, so they are going to provide complementary data on the positions and motions of the stars and the distances. And they do have spectroscopy at a low resolution, so they can get general idea of the motion, the Doppler motions of the stars, and some general idea of the overall enrichment of the stars. Where APOGEE comes into play is that we can actually then add information about the very specific chemical compositions of the stars, which with Gaia data we can place very accurately in the galaxy, more accurately than perhaps we can do with APOGEE data alone. And so together they work to make a much better picture, a much clearer picture of the populations of our galaxy.
Okay. Does anything come in on the web? All right, well, that's okay. We're allowed to finish a few minutes early. I want to thank the Sloan team in all its many acronymal variations. We'll have a test later what all these acronyms mean. Thanks to Connie, Rockosi, and Daniel Eisenstein, Jian, and Steve Majewski, and of course Michael Wood-Vasey for helping to MC the proceedings. We're only halfway through, so I know you're starting to flag a little, but you've got to find a way to get your energy up. One way is to attend the press reception if you're a press registrant this afternoon, 5:30 next door in room 309. The American Institute of Physics is celebrating the awarding of the 2014 Science Communication Awards. We'll be celebrating Alex Witza and Lee Billings, who are both here among the press corps. And then, as if that's not enough celebrating, our no-host press dinner convenes about 7 o'clock at Cutter's Crab House. It's pretty easy to get to. It's about a half a mile from here. You just walk down Pike Street to the end and turn right, and eventually you'll bump into the restaurant. There are some maps on the bulletin board in the press room, and also some extra copies in front of the mailboxes, and if you need another one, just ask. So tomorrow morning's briefing will be on the superstar Eta Carinae. That convenes at 10:15 a.m. right here. And then, of course, we have another briefing tomorrow afternoon and 2 more on Thursday. And I think that's it, unless you can remember any other announcements. Okay. Well, thank you all very much, and we'll reconvene in the morning. So before you take off,